How to get a 5 on the AP Calculus exam first and foremost requires knowing your content. And this is the best video to get a review of what you need to know for Unit 1, Limits and Continuity. And I would love to hear in the comments section below, which of these 8 do you feel like will be most challenging for you? And also in the description, I provided a link to various videos where I go specific into these topics. So give those a look as well, and grab a notebook, grab some paper, grab something to write with, and follow along with me. So the first one you need to know for Unit 1, Limits and Continuity, is you need to know what actually is a limit. Let's first talk about limit notation. So the way you write a limit is you would say the limit as x approaches c of f of x. So let's talk about what this notation means. This means that you are looking for the y value that f of x approaches. That's going to be a key word that I'm going to keep referring to. The value that f of x approaches as x approaches c from both the left and right sides. Okay, so it's the y value the function approaches as the graph approaches that x value, again, from both the left and the right-hand sides. That's what a limit is. So let's talk about how to find a limit from a graph. So if I were to give you a graph of f of x here, and I were to label this as c, again, the limit is the y value that the function approaches from both the left and right-hand sides of c. So as I come in here on the left side of c, and then I come in from the right side of c, as I come in from the left and right-hand sides, this value right here is going to be your limit, and I'll call that L. So the way that we would write this out is I want the limit as x approaches c from the left-hand side of f of x, if this is the function f of x, to equal the limit as x approaches c from the right-hand side of f of x, and I want both of them to equal this limit L. Now, from the left and the right-hand side, you could be approaching a singular point, and then L would be the limit. Or you could be approaching a hole and then the limit would still be L. So it's not what the function equals at that c value. It's the y value that the function approaches from both the left-hand side and the right-hand side. So what if this graph were to look a bit different? So let's say you had a graph, and as f of x approached c from the left-hand side, you're approaching this y value, and from the right-hand side, we were approaching this value. In this case, the limit would not exist, and that's because the limit as x approaches c from the left-hand side of f of x does not equal the limit as x approaches c from the right-hand side of f of x. Therefore, the limit as x approaches c of f of x does not exist. So once again, find the limit from the graph. Make sure to look at the y value that f of x approaches from both the left-hand side and the right-hand side of c. Let's move on to number 3. How to find a limit from a table. And we're going to use the same ideas that we used for number 2, finding a limit from a graph. So now we just have a table, and instead of a graph, we would have x values, and then we would have f of x values. And let's say we want to find the limit as x approaches c once again. Okay, so just another reminder that I would need to look at the limit as x approaches c from the left-hand side of f of x. Therefore, I am looking at these y values right here of f of x as I approach the x value of c. So I am looking at these values and looking for trends. You know, what number am I trending towards on the left, and making sure that that equals the limit as x approaches c from the right of f of x. So as I approach this way. The numbers here are approaching the same value as the numbers here. Now notice I am not looking at what this value is right here. It does not matter what is the value at C. It could not exist. You could have an error in your calculator, anything like that. But as long as the values, as long as the y values from both the left-hand side of C and the right-hand side of C approach the same value, the limit does exist. And that limit would, for example, equal L. So therefore then we can conclude that the limit as x approaches C of f of x does equal L. Now for number 4, this is a biggie. Find limit using algebra. So in this case, we are finding the limit as x approaches C of some function f of x. Whenever you are given the function f of x, what I always encourage you to do is use direct substitution first. All right, so that's what you're going to start doing. You're going to plug in the C value into the function for all x values and see what number you get. If you get a finite number, that's the best one, then you are done, and that's the value of the limit. That must mean that our function is continuous at that x value, so you can just plug it in and get your value. Okay, another case you could have is you could have a non-zero number divided by 0. That tells you you have a vertical asymptote at that C value. Again, this tells you a lot about the function, because if we have a vertical asymptote at C, there's only one of two situations that could happen. As you approach from the left-hand side, you can only approach positive or negative infinity. And then as we approach C from the right-hand side, again, you can only approach positive or negative infinity at vertical asymptotes. So therefore, your answer will either be positive infinity or negative infinity. So how do you determine then from the left-hand side whether you're approaching positive or negative infinity, and from the right-hand side? What I like to do is I like to plug in numbers just to the left and right of C. So what you would do, let's say C is 5. You would plug in, think about plugging in 4.99, a number just to the left, and seeing does f of x go to positive infinity or negative infinity. And then likewise for choosing a number just to the right of C. Again, vertical asymptote, the answer can only be positive infinity or negative infinity. All right, now let's say instead of non-zero number divided by 0, what if you were to get 0 divided by 0, or you were to get any version of positive or negative infinity divided by positive or negative infinity? Again, this is all after direct substitution. These forms are all called indeterminate forms. And again, it can tell you a lot about a function. Okay, so we know we don't have a vertical asymptote there. For example, you could have a hole if you had 0 divided by 0 and things like that. So in this case, if you get some of the indeterminate forms, I want to talk about what you can use. You would have to use various forms of algebraic strategies. All right, and again, this is the biggie. There's various algebraic strategies we could use, and it all depends on what your function is. So to go over some of these algebraic strategies, first, if you have a polynomial divided by a polynomial, a lot of times those can be factored. So you'd want to factor, then you'd want to simplify, then you would use substitution and plug in your value of C. All right, another thing you could do is if you have a polynomial divided by a polynomial is you may have to use division. You may have to use a division first to simplify this rational function, and so you may either use long division or you may use synthetic division. So simplify first using division and then plug in your C value, then use substitution. All right, let's see what else you could do. You may have to use the strategy of multiply by the conjugate. Now, how would you know when to multiply by the conjugate? I would say that's when you have a radical in your problem. Oftentimes, you can multiply by the conjugate. Basically, you're multiplying by the equivalent of 1, so you're not changing the problem, you're just simplifying, rewriting it so that you can plug in the C value after all. And another one you could have is you may have to multiply by the least common denominator to the numerator and denominator. So again, how would you know when to use this strategy? I would use this strategy when we have a complex fraction. So lots of algebra strategies there, and the whole point is so that we can rewrite that function so that we can plug in C to find the limit. All right, so that was a biggie, find limit using algebra. All right, let's talk squeeze theorem. The squeeze theorem is if h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing C, and the limit as x approaches C of the lower function is equal to the limit as x approaches C of the upper function, so those limits are both equal, let's call that limit L, then you know that the limit as x approaches C of the middle function also has to equal L, because this function is squeezed in between the other two. So if the lower function approaches the limit L, let's call that h of x, and then the upper function from both the left and the right hand side also approaches the limit as L, well then if f of x is squeezed in between the other two, f of x also has to approach that same limit of L. But what's really important here that I want to go through with you is how to justify your answer using the squeeze theorem. All right, the first thing you want to do is you want to verify your conditions. So you want to verify that one function is in fact squeezed in between the other two functions for all x values. Then you want to find the limits of the upper and lower functions. Okay, you want to show that the limit as x approaches C of the upper function is equal to the limit as x approaches C of the lower function. And then finally, you want to make a conclusion about the middle function's limit. Okay, so verifying your conditions that the middle function is in fact between the other two, and if the other two go to the same limit, well then that middle function has to go towards the same limit. Let's move on to number 6, finding limits at infinity. So for this one, we are finding the limit as x approaches infinity of f of x, or we may be asked to find the limit as x approaches negative infinity of f of x. Now notice in both of these where x is approaching infinity or x is approaching negative infinity. What these are asking us about these are asking about the end behavior of the function or what's happening at the far ends. Also, you could be asked to find the horizontal asymptotes. This would be the same thing. So you're looking for what's happening at the far ends of the graph. I'm going to go through the 3 scenarios that could happen if you have a rational function. So for rational functions, one case could be that the degree of the numerator is less than the degree of the denominator. And if this is true, then the limit as x approaches infinity or negative infinity of f of x will be equal to 0. So that will be the horizontal asymptote of the function f of x. Okay, another case you could have is that the degree of the numerator is actually equal to the degree of the denominator. And in that case, the way that you'd find the limit as x approaches infinity or negative infinity of f of x is you would take the leading coefficient of the numerator and divide that by the leading coefficient of the denominator. All right, and in both of these cases, this would give you the horizontal asymptote of the function. And then the last case is number 3, and you can probably figure it out by now. This is if the degree of the denominator is greater than the degree of the numerator. Okay, in this case, this means your function, f of x, is either approaching infinity or negative infinity at the ends. Next up, number 7, is the definition of continuity. And the definition of continuity has 3 steps to it, and it's how to determine whether f of x is continuous at this specific x value. So I would say that f of x is continuous at x equals c if the following 3 conditions are met. First of all is that f of c has to exist. What does that mean? That means on a graph and at the x value of c, the function has to exist there. So there can't be a hole or a vertical asymptote or something like that. So we have to have a point right there at the x value of c on the function. Step number 2, the limit as x approaches c of f of x has to exist. Let me put exist. Let me add an s right there. So the limit as x approaches c of f of x exists. Now remember, for a limit to exist, we talked about that kind of up here on some of the top ones. The limit as x approaches c from the left-hand side of f of x has to equal the limit as x approaches c from the right-hand side of f of x. So again, the limit coming from both the left and right-hand sides of c has to be equal. Now before I add this to the picture, I actually am going to jump to step 3. And step 3 is that step 1 has to equal step 2. So the value of the function at c has to equal the limit as x approaches c of f of x. So what I mean by that is that as I approach c from both the left-hand side and the right-hand side, those limits have to be equal, but they also have to equal the value of c. And as you can see here in this picture, this function f of x would in fact be continuous at x equals c, and that's how we would use the 3 steps to the definition of continuity to find this. Let me go through different discontinuities and talk about what they're called, and also talk about like which of these it fails. So let's first talk about something called a removable discontinuity. And this is also known as a hole. So let's take a graph, and we would have, let's say we had this scenario. Let me connect that right there. All right, so we've got this scenario. This is called a removable discontinuity, also known as a hole. So we can already see step 1 is not true. F of c does not exist. There is, a hole there. But even if I put something like this, let's see what step this fails right here. Well, f of c does exist. Step 2 does not fail. We can see the limit exists because as the limit as x approaches c from the left and the limit as x approaches c from the right are in fact equal. But you can see this one would fail step 3 because those are not equal to each other. So that's a removable discontinuity. Then we also have non-removable discontinuities. And there are 2 types to this. One non-removable discontinuity we could have is a vertical asymptote. And maybe the function, looks like that at the vertical asymptote. You can already see in this scenario, step 1 fails. F of c does not exist because we have a vertical asymptote. So a vertical asymptote is a type of non-removable discontinuity, and another type of non-removable discontinuity is a jump. And this would fail step 2 because oftentimes at a jump you can see a point right there. So f of c does exist, but the limit as x approaches c from the left does not equal the limit as x approaches c from the right. So here we've gone through the steps of the definition of continuity as well as some common discontinuities. And now we've made it to the last one, the intermediate value theorem. And the intermediate value theorem, sometimes abbreviated as IVT, but I would not abbreviate it on the AP exam, just write out the whole thing. So the intermediate value theorem is used to prove a y value exists. And here is the intermediate value theorem. If f is continuous on the interval a to b, on the closed interval a to b, then f of x takes any value between f of a and f of b. And the most important part of the intermediate value theorem is you have to show that f is continuous on the closed interval. You cannot apply this theorem unless the function is continuous. So to kind of show you on a picture what this means is, let's say I have the interval a to b and f of x is continuous, and then let's say f of a is down here, and let's say f of b is up here. And as long as the function's continuous, this function has to take on every y value in between f of a and f of b to get from point A to point B, literally. And so you could go outside of that range, you could go above, you could go below, but it does have to hit at least every y value in between f of a and f of b. But I'd like to show you how you would justify an answer using the intermediate value theorem on the AP Calculus exam. Step 1, you first need to verify that you can even use the intermediate value theorem. So you need to verify that your function given in the problem is continuous on the closed interval that you are also given in the problem. So make sure that comes first. Then you would need to find the y values at the endpoint. So find f of a and find f of b using the values of a and b that are given to you in the problem. Then make sure to check that your desired value is between those. So maybe you want to know if y hits the y value of 2. Well, make sure 2 lies in between the two y values at the ends. And then finally, you write a sentence to justify your answer. So since the function given in the problem, whatever that is, f of x, g of x, h of x, something else, is continuous on the closed interval given in the problem, and f of whatever your a value is equals this number, and f of whatever your b value is equals this number, then the intermediate value theorem guarantees that, and then you would state your conclusion. All right, that is it. That is all 8. These are the things you need to make sure you know for Unit 1, Limits and Continuity. Come back to this video right before the AP exam. Go through these 8 things. And I'm telling you, if you know these 8 things for Unit 1, you are closer to getting a 5 on the AP exam because you know your content. Thanks for watching, everybody. Give it a like or subscribe if you haven't already to see future videos to help you on the AP Calculus exam. Have a great day, everyone. See you in the next video.